Hello viewers, I discuss today the Bessel's inequality, and at first if we are considering this an orthonormal set in a Hilbert space E1, E2, En, if we consider it, and if x be any vector in H, then we are proving this inequality. This is a very much important part and famous inequality. If we watch it, summation I runs from 1 to up to n mod of x dot ei whole square is less than equals to norm of x whole square, where x be the any vectors and e1, e2, en is the orthonormal basis set, and this orthonormal set in Hilbert space H, and x be any vector in H. Then we proving this inequality. And the viewer who are watching this video first time, they subscribe this channel and press the bell icon to get all the notification and latest subject of my video, and keep watching this video without skipping. Let's watch how to prove this result. Now we are considering a vector in this form y is equal to x minus summation I equals to 1 to up to n x dot ei. It is a type of considerations when we are using this type of consideration in Graham-Smith orthogonalization process of linear algebra. This is a specific considerations. If we are taking in this way, we are proving our desired result. Otherwise, it is not possible to prove our desired result. So, we are considering in this manner. Now, let's watch till the end of this video how to prove this result. Now, we have here norm of y whole square. That means y dot y from the property of inner product, and we know already, and substituting this value of our consideration as x minus sum of I equals to 1 to up to n x dot ei minus x dot of x minus sum of j runs from 1 to up to n x dot ej. But if someone asks this question, why I put another variable j here in the second expression, because to prove our result we are using this dummy index, and frequently we use in many types for the dummy index to prove our desired result. It is needed actually, and if we are going step by step, we clear our idea how we use this result, how we use j not I in the second cases. Now we are producing our result and using the property of linearity as x minus sum of j runs from 1 to up to n x dot ej to up to ej. That means here x dot this total result. So x dot this total expression minus this expression dot this total expression x minus it. This result we are using. Now we are using the property of splitting, another linearity property. So it will be x dot x minus x dot this, and here also minus of x dot this minus plus. So it will be plus of this dot this. And now we are using x dot s is mod x square, and here if we are taking in this manner x dot ej, it will be bar, that's conjugate. That's why it takes a conjugate x dot ej, j runs from 1 to up to n, x dot ej whole bar, complex conjugate in Hilbert space, and it will be x dot ej in this manner. Here we are writing x dot ei x dot ei, and it will be our result of ei dot x. So ei dot x can be written as x dot ei bar, complex conjugate format. Here it will be writing ei dot x, so ei dot x can be written as x dot ei whole bar. And our next result, sum of I runs from 1 to up to n x dot ei, and sum of j runs from 1 to up to n x dot ej. So it will be sum of I equals to 1 to up to n, and here if we are writing sum of j equals to 1 to up to n, it will be x dot ei dot, and here it will be written x dot ej multiply by ei dot ej in this format, these two. And we are writing this result mod of x whole square sum of j runs from 1 to up to n, and it will be conjugate and this result, so it will be mod of this whole square, mod of inner product of x dot ej whole square. minus here also write mod of x dot ei whole square, and it will be write as sum of I equals to 1 to up to n, sum of j equals to 1 to up to n, and x dot ei, x dot ej, ei dot ej. And if we now produce writing all the same expressions as written, and on the last expression we are operating, and last expression will change. If we are changing this dummy variable, and here also it is observed, if we are taking all j as I for the sake of simplicity and for the proof of our result, then it will be replaces as I, dummy variable. So j is changed with I. So I runs from 1 to up to n, x dot ej, so it will be turned to x dot ei. Here also changes for I. Yes, it is same expression as we write. And next terms, for the fourth term of the expression, that will be changes. J is turned into I. So sum of I equals to 1 to up to n, x dot ei, and here also x dot ei, and ei dot ei. So ei dot ej turns into ei dot ei. That's norm of ei whole square, that is 1. Certainly, so it will be abolished. And in the next step, we are writing all this expression keeping as same. It is minus of minus, so 2 of minus 2 of same expression, minus 2 of I runs from 1 to up to n, x dot ei whole square plus x dot ei whole square. This will be turned into 1. So it will turn into norm of x whole square minus sum of I equals to 1 to up to n mod of x dot ei whole square. And this is turned into this result. So norm of here we consider it will be norm of y whole square simply turn into norm of x square minus sum of I runs from 1 to up to n mod of x dot ei whole square. Now let's watch what happens. As this will be norm of y whole square, so it will be greater than equals to 0, and finally so this turn into this expression mod norm of x whole square minus sum of I equals to 1 turns from 1 to up to n x dot ei whole square. So it will be non-negative term and certainly greater than equals to 0. And that proves our desired inequality, that norm of x whole square equals to minus sum of I runs from 1 to up to n mod of x dot ei whole square greater than equals to 0. That is norm of x whole square greater than equals to sum of I equals to 1 to up to n mod of x dot ei whole square. And in other words, we are already ensure our inequality and our desire proved of this result. That's sum of I runs from 1 to up to n mod of x dot ei whole square is less than equals to norm of x whole square. We finally prove our desired result. So in this way we end our discussions. If you like this video, like it, share it, and don't forget to subscribe.